from Germany. Very good mobile. Yeah, right. Yes, we're working on double part dialysis and expert on the 4-point functions, which is the frontiers of lattice calculations, and this neutral electric dipole moment is one of the examples.
Yeah, I mean, it's not a 4-point function in that sense. I was treating it in the past, but okay, yeah. Counts, yeah.
Okay.
Yes, yeah.
Good.
Bilocal electric element, yeah. All right, thanks for the introduction. So, right, so this is one of the two big topics that I'm working on here in Berkeley together with Keh-Fei and Liu. It's about the electric dipole moment of the nucleon, which you want to calculate on lattice QCD. So, yeah, I started working on the project half a year ago. Right. And, oops. Yeah. Right. As I said, my collaborators, 2 of them are present today, Keh-Fei and Liu. Other one, Jan Yang, is in South China University. Yeah, so far, I mean, we have 2 publications on this topic. If you want to have a look at it, so you can find most of the plots therein. Right, so let me start a little introduction. So why are we interested in the electric dipole moment of nucleons? So there is this question, why is there more matter than antimatter in the universe? Why is there a measurable positive baryon number? So, I mean, the recent number, one of the recent numbers that has been published is the number of baryons. So the number of baryons minus the number of antibaryons divided by the number of photons in the universe is approximately 6 times 10 to minus 10. Right. Order to this, I mean, in order that is possible, Sakharov defined, opposed these 3 conditions known as the Sakharov conditions. Namely, you need violation of baryon number conservation in order for this to happen. You need breaking of CP symmetry, so the mixture of charge conjugation symmetry and parity. And this has, I mean, in order for this to happen, you have to have a fermion non-equilibrium. So, right, all of what I'm going to tell you in this talk is about the second point, the breaking of CP symmetry. There are 2 possible sources in the standard model where CP can be violated. One that is actually part of the standard model is in the electroweak sector. It's through the CKM matrix, and they are now going for the leptonic sector, the PMNS matrix, and the theta-term, which is a possible extension of the QCD sector in the standard model. So, however, these 2 effects are by far too small to explain baryogenesis. But yet, the study of theta-term is essential in order to understand potential CP violations in the standard model, so that we can tell apart for instance, if we measure electric dipole moment of the nucleon, we have to know what's part of the standard model. It will tell you what is the beyond standard model contribution to that, which might be responsible in the end for baryogenesis. Right, and I already mentioned it, one of the proxy quantities that gives us access to the theta-term and measurements of the theta-term is the electric dipole moment of nucleons.
I have a question.
Yes.
Are there sources in the standard model to violate baryon number conservation?
No.
I thought it was just B minus L that's concerned.
Yeah.
But B itself is also concerned.
Yeah. Correct. I mean, if you look at the Lagrangian of the standard model, you always have, there's nothing that can violate baryon number.
Does the neutrino's double beta decay violate baryon number?
No.
Don't think so.
It's left on number, but 2 units.
I mean,
So
you
wait,
need,
if it's left on number.
you need to have something in the Borg sector. I think it's not,
It's still fine, it's B minus though.
maybe that one, yeah, but yeah. I mean, for baryons, you need the quarks, basically. Yeah. Right, okay, so this is my outline. I mean, I have 3 parts in this talk. First, I will talk about CP violation and the theta-term in general. I will point out that chiral symmetry is important in this context, which is why I will discuss lattice QCD and chiral symmetry in a separate section of this talk. And the third part of this talk will be about our calculation regarding electric dipole moments on the lattice. Right, so let's go into the first section, CP violation. As I already said, in the standard model, CP is violated in the electroweak sector. However, we want to look for CP violations in QCD. The standard model QCD-Lagrangian, as we have it formulated right now, preserves chiral symmetry, CP symmetry. But there is a possible extension, namely the theta-term, which is a dimension 4 operator that you can add to the Lagrangian. And if you consider physics beyond the standard model, and you build an effective theory at standard model scales, basically, that can also induce CP violating effects, which look like higher order terms in the QCD-Lagrangian. So if you formulate a low energy effective Lagrangian at a scale of 1 GeV, so you integrate out everything that's heavier than the Strange-Cook mass, then you can write down the effective Lagrangian like that. You have a Lagrangian that knows only 4-dimensional operators that look like the theta-term, or the theta-term itself. But you also have 5-dimensional, 6-dimensional operators that even higher dimensional. I think the series continues. So where the 5-dimensional operators would be something like quark or lepton electric dipole moments, Kerr electric dipole moments, and so on. And the dimension 6 operators would be something like a Weinberg operator. We do not want to go into too much into detail on that. Just want to tell you that these terms also exist. But as I said, in this talk, we will focus on the theta term. So if you go further down to the nuclear scale and make an effective theory that is relevant at the nuclear scale, then you basically find 3 terms in the effective Lagrangian. It's basically the electric dipole moments of nucleons and the electron, and CP violating effects in the pi and n coupling, and also CP violating effects in the electron-nucleon interaction. In this talk, I will basically refer to both of these, to both of the first terms, electric dipole moments of the nucleon and CP violating ion coupling. So, if you want to have a reference for review for all these points, there is some by Pospelov. Right. So, what is the theta term? So this is here I show you the QCD-Lagrangian as we have it right now in the standard model. So basically the fermionic part with the quarks, with the gauge covariant Dirac operator, the mass matrix, and the free gauge part basically, which conserves CP symmetry. And the theta term violates it. Theta term is consists of a constant that we call theta bar in this case. I will explain the difference between theta and theta bar very soon. And Q is the so-called topologically charged. So it contains the field strength tensor of the gluons and its dual version basically. So there is, I already mentioned it, there is some ambiguity here between the mass term here and the topologically charged term, which becomes clear when you consider chiral transformations, which look like that. Because this, if you make a chiral transformation like that, that also leads to a change in the measure of the path integral, which again leads to the anomalous Ward identity here. So if you have a matrix element of a flavor singlet axial vector current, this is not conserved, but changes with respect to that have ends up in these terms here, where PF is the pseudoscalar density, MF is the mass of the corresponding quarks, and this is basically the change of the measure in the path integral, which involves again the topological charge. And through this identity, we can use this identity basically to shuffle around phases that can arise formally in the quark mass matrix. So you can use chiral transformations to change the constant theta and instead have a phase in the quark matrix. So we do things other way around. Basically, if we start with some initial theta and assume that the quark matrix in general can be complex, then we redefine it by making a chiral transformation so that the quark matrix is a real, and this defines basically theta bar. On the other hand, this anomalous Ward identity tells us that we can always find a chiral rotation so that the theta-Lagrangian takes this form, where M star is this I don't know if it has a name. It's just this combination of all the quark matrices basically. And the thing is, if one of the quark matrices is one of the quark masses is 0, then you can always find a chiral rotation so that the theta term vanishes. You can completely rotate the theta term into the quark masses basically, which implies that we have no net CP-violating effect in this case. So the chiral limit there is no CP-violating effects in the end then. Right, so so as I said, at the nuclear scale, we have CP violations can lead to non-vanishing electric dipole moment of nucleons, and corresponding terms would look like that. You have psi bar psi, and between you have you have gamma mu basically, the anticommutator, and gamma 5, which is then coupled to an electromagnetic field. And so what do we have to do in order to calculate these things in QCD? Well, we consider a matrix element of the nucleon of a vector current and make a Lorentz covariant decomposition and see if you find basically, if you can identify a term which is proportional to something like that. If you have CP and P conserved, the decomposition looks something like this. So U bar U are basically Dirac spinors, and you have these Dirac structures in between, and F1 and F2 are called Dirac and Pauli form factors. So Dirac form factor corresponds to charge, and Dirac and Pauli form factors together contribute to magnetic moment. But if CP and P is conserved, there's no term which is proportional to something like this here. However, if CP and P are violated, we have two extra terms, the F3 term and the FA term. FA is the so-called anapole form factor. And this is the important term in our case, the F3 term basically. And that has the required gamma 5 here. So the dipole moment can be identified by this ratio F3 over 2m at q squared at zero momentum transfer, basically. Right. Let me just summarize what we know from experiments about electric dipole moments, how they're measured. So basically, you use spin polarized nucleons and measure the precision around an applied electric field. So it's advantageous to use a neutral particle like the neutrons because you can apply very strong electric fields without any complications. But so far, we only can give an upper experimental bound. So this is one of the recent measurements. So you see the mean value is still 0, but yeah, it has an error bar. So it might be if we increase precision that we might measure something at some point. Experiments are still ongoing. I've listed some of them here. And we expect them to increase the statistics by orders of magnitudes within the next few years. But you also can do measurements with charged particles in storage ring, for instance. A close experiment at Jülich. Right. So there's another part of the effective Lagrangian nuclear scale. I already mentioned it. It's the CP-violating pi-n coupling. That can be treated in heavy baryon chiral perturbation theory. There are some references regarding that. And this Lagrangian basically consists of 3 terms, where g bar 0, g bar 1, g bar 2 are the low energy constants. And also in heavy baryon chiral perturbation theory, you can give this relation between g0 and theta bar, which relates the mass difference between neutrons and protons and the mass difference between the up and down quark. Right. Moreover, there exists SU3 chiral perturbation next to linear order result for g bar 0 by Andres collaborators, actually. Yeah, and they obtained that result here. Okay. So this is something that is important in the context of lattice calculations, because on the lattice we usually we use unphysical quark masses, which simplifies the calculations. And in this project, actually, this is an advantage if we treat chiral symmetry correctly, because we can employ the anomalous water density again. I already mentioned it implies that the CP-violating effects vanish at the chiral limit. So if we, there was a calculation in the past in partially quenched KPT, so they treat basically the valence quarks and the C quarks separately, form basically a multiplet of 4 different, more quarks, but I mean, the C quark and the valence quark are basically different separately in this context, and they derived this formula here for the dipole moment. So here you have again a global prefactor in terms of theta bar. Right, as already said, you can use formula like that, which depend on the masses of the pi, where it's distinguished between the valence quark masses and lattice calculations. In order to interpolate. However, you see this is a kind of very complex formula which has a lot of terms, and on lattice usually you only have a few points, so we have to reduce things a bit. And in our project, we chose this form here, which contains this log term of n pi, the valence quark mass of the pion mass resulting from the valence quark mass squared and the corresponding mass of resulting from the C quark mass, basically. And there's
I have a question.
Yeah.
In the simplified version, what are the main things you're neglecting in the more complex version?
For instance, I did not read all the details in this paper, I have to be honest, and I did not make the choice. But for instance, here there's a distinguishment between a pion mass and a goldstone mass. This is basically treated as one term here.
Mm-hmm. Okay.
Just because it reduces the numbers of degrees of freedom. Yeah. Because on the lattice we have only a few data points. If you have many terms like that, we cannot fit usually.
It would be interesting to see the chi-squared for each of those, because if it is a better model with less degrees of freedom, then you might get something closer to one. Interesting.
Yeah, I mean, there's room for improvement, certainly. If anyone has suggestions on that. I mean, I will show you plots on these extrapolation. Maybe someone has a feeling on how to do things better.
Also, I have
a
question. So the C1, C2, C3, those are just LECs you have to fit.
Right, exactly. I mean, partially quenched KPT, they have certain prefactors here that do not exist in the lattice. Here, in our case, we just have prefactors which are basically fit variables. Yeah, the important feature here is that you have different behavior with respect to the valence pion mass and the C pion mass, because if you decrease the C pion mass, this term decreases as well, but if you decrease the valence pion mass, the term increases. This is something we will see in the lattice table later.
Are there ways to, are they independent from each other? Are you able to change the valence?
Yes. Sorry, I mean, this is the important thing, because the C pion mass is defined by the gauge ensemble, basically. Okay. The valence pion mass is the pion mass that is relevant for your propagators that you plug in the lattice calculation. Right. Okay, let me go on to lattice QCD and chiral symmetry. So most of you are familiar with or have seen lattice calculations at some point, but nevertheless, not all of you are working mainly in lattice QCD. That's why I give a little introduction to lattice QCD first. So we calculate expectation values of operators by directly evaluating Feynman path integral on a discrete and finite space-time, which is our lattice. The advantage is it's finite, so it has infrared regularization. It has finite lattice spacing, which means we have a UV cutoff. The fermionic part, so the quark fields, can be analytically evaluated because they're Grossman variables, and that results in these so-called big contractions. Moreover, we have to go to a Euclidean space-time, because then this exponential here, we get rid of the I in exponential, so that this factor here turns into a suitable weight for Monte Carlo integration, which is the method we choose in order to evaluate the remaining integral over the gauge fields. So basically, this is the quantity we are left with, integral over the gauge fields, the fermion determinant, the exponential of the action, and our observable of interest. Yeah, and this we do by Monte Carlo integration. So we choose gauge ensembles that are distributed according to the weight defined by this term here in the middle. Right. So we have to discretize our action, and this we do by putting the fermions on the grid points and replacing derivatives by symmetric differential quotients and integrals by sums. We have to restore gauge invariance by putting in these gauge links between the grid points. And we have to add the pure gauge part, which we do by, for instance, by adding this placket term, which corresponds of a circle of gauge links, basically. So if you do this in a naive way, we run into a problem. If you consider the massless propagator that we just constructed here, then we see it has 16 poles instead of 1. Namely, also on the edges of the Brignois zone. So that means we have 15 unphysical doublers, which we have to get rid of. And yeah, here we run into the next problem, because that becomes clear if we consider chiral symmetry. I've already showed you how it looks like. Basically, it's defined by this rotation, and from this rotation you can derive that the Dirac operator commutes with gamma 5. But this is not true once we try to get rid of the doublers. For instance, by adding this Wilson term, because it has this term here, which is a mass-like term. It makes the doublers heavy and decouples them from the theory. But it also breaks chiral symmetry explicitly. So you might ask if is there another way to do that, to remove the doublers and yet have chiral symmetry? And there's a no-go theorem actually, so by Nielsen and Lemire, so it's not possible to formulate doubler of the discretized theory, which is chiral symmetric. But there's a way around. We have to modify chiral symmetry. So we have to invent a lattice version of chiral symmetry. And this is given by the so-called Ginzburg-Wilson relation. So instead of saying that gamma 5 commutes with the Dirac operator, you say that there is a remainder term here. And you see, if you take the lattice spacing A to 0, it recovers the continuum chiral symmetry. But of course, it's not the actual chiral symmetry that we have, it's some sort of lattice version chiral symmetry because the rotation has a modified form here. So what we have to do is we have to find a discretization that fulfills this relation. And I'm aware of two solutions, namely the overlap fermions and the domain wall fermions.
So the A is lattice spacing. So you
Yes.
only recover true chiral symmetry in the continuum.
Right,
Okay.
right. But it's not a problem because, I mean, as long as you can work out the same rules that you can derive from chiral symmetry from this version, from this version of chiral symmetry, you're fine.
Well, it has been shown that all the current algebra relations are satisfied at finite A.
Okay.
And you can show that the overlap propagator just behaves like a quark propagator, exactly the same form as the continuum. So everything is, when you look at the overlap operator, all the formulas is almost exactly the same thing as the continuum.
Right, I mean, on the next slide, I will show you the important relation that is also fulfilled. Right, so I already mentioned that overlap fermions are a solution to the Ginzburg-Wilson relation. And they are basically defined by starting from the Wilson operator, multiplied by gamma 5, take the matrix sign function, which is a bit complicated to calculate, which is why overlap fermions are difficult to treat on the lattice. But it's completely worth it, as we will see in the following. Right, so this is the definition of the overlap operator. It has certain properties that are different from other discretizations. For instance, they are not ultralocal. Ultralocal means that the Dirac matrix is a sparse matrix with only entries at the next in the upper or lower neighboring diagonal, and this is not the case for the overlap operator. Makes things a bit more complicated, but it can be shown that it fulfills the anomalous Ward identity exactly on the gauge configuration level. And this is the important identity that we want to employ in order to do our current interpolation. Right, so again, I mean, Q is a topological charge here. And next advantage is, since we have this lattice version of chiral symmetry, which we fulfill with our overlap fermions, we can also derive a lattice version of the Atiyah-Singer index theorem, which relates the topological charge to the difference of the left-handed zero modes of the Dirac operator minus the right-handed zero modes of the Dirac operator, which can be expressed by this trace of the overlap operator. So this will be our implementation for the topological charge on the lattice. Okay, just a few words on that. How do we actually calculate hadronic matrix elements on the lattice? So remember, the lattice we have Euclidean time, and we can create our nucleons by operators that have suitable quantum numbers, have some overlap with the nucleons itself. And this is the current of interest. In our case, it would be a vector current and the topological charge. And now you can insert a complete set of eigenstates and consider time evolution, which involves Hamiltonian. Since you have eigenstates here, you can pull out the Hamiltonian, and this ends up in these exponentials here, which fall off with increasing separation of the times. So if you put if you make the time separations between these operators large enough, you're only left with the ground state. So this is how it works on the lattice, basically. And if you want to isolate this matrix element, you have to divide by a so-called two-point function, which only involves the interpolating fields of the nucleon. Right, and that brings me to the calculation of the EDM on the lattice that we perform. So first of all, we have to put the CP-violating QCD action on the lattice. And there's a little difficulty, namely, in Euclidean time, you get an extra factor of I here. So this is the CP conserving QCD action, which is well studied on the lattice. This is the additional term which violates CP. And this you cannot simulate directly because it causes a sign problem. And also you would have to generate gauge ensembles for this action, which you want to avoid because it's expensive. And the workaround is to consider either part of small and expand around the CP symmetric case. So this formula basically. Right. So this we already had. This is the matrix element we want to calculate in the lattice. The form factor 3 is what we want to extract because it gives us the electric dipole moment. So all we have to do is we have to calculate this matrix element in the CP conserving case, which requires the usual matrix element of the electromagnetic current. And we have to calculate this matrix element in the CP-violating case, which involves the topological charge, according to what I've shown you in the slide before. And F3 can be extracted by calculating this combination of matrix elements. It's a bit complicated to derive. I hope you believe me that this indeed equals F3 in the end. Right, and there's another observable that we can consider here, namely the CP-violating binding coupling, which is almost the same matrix element as for the I mean, technically as for the nucleon dipole moment, but the only difference is that we have a gamma phi instead of a gamma mu here. And that can be related to the low energy constant G0 by assuming some dipole dominance model. All right. So let's do calculation. As I said, the fermionic degrees of freedom are already integrated out analytically, and this leads us to these two weak contractions here. So we have a connected contraction and a disconnected contraction. And this orange part here is the topologically charged. So, I mean, this is a bit technical here. This is only interested for people actually doing lattice calculations by themselves. Just some information for you. At the source, we use a Z3 grid source. So we have 2 grid points in each direction. And we use Lohmann substitution in order to speed up the convergence of the stochastic noise here, basically. In the connected contraction, we have an additional stochastic insertion at the sink. And we have to deal with the problem that if you consider bilocal quantities like that and make the separations between the currents large enough, then the signal is basically gone, but the noise still increases. And this we avoid by employing the so-called cluster decomposition error reduction method, or abbreviation CEDA, which basically looks like this. So here you have basically, this is again the connected three-point contraction. This would be a 2-point contraction. And so basically what we do here, once the signal saturates, I mean, we have this sum over all the space-time points at the sink, and also for the current, and also for the topologically charge. And if the distances are large enough so that basically the signal saturates, but only the error increases, we just cut the sum there. This is basically the entire idea of CEDA. Right. Then yeah, so this is basically these are basically the gauge ensembles that we use for our lattice calculation, and have been generated by the RBC UK QCD collaboration. I mean, the important thing is here we have different C-quark masses here, which are basically defined by the gauge ensembles. And yeah, this is the current status basically. Currently, I mean, the current analysis includes these ensembles here. It's a 24 cube times 64 lattice in this case. Simulations for the next larger lattice, the 33 cube lattice, is underway, also with different C-quark band masses. And for each of these ensembles, we perform the calculation for various valence quark masses. So remember, the valence quark mass is basically it's basically a parameter for the propagators, which we use to build up the contractions. All right, and yeah, here are some results. So what you see here is the electric dipole moment divided by theta. 4 different quark masses. On the x-axis, you always have the C-quark mass. On the left-hand side, you see the case where the C-quark mass and the valence quark mass are equal. And on the right-hand side, you see you have several points for different colors. And okay, actually I have to correct myself. The x-axis is the valence quark mass, not the C-quark mass, sorry. And yeah, you see basically, I mean, different color means different C-quark mass and different position with respect to x-axis is the different valence quark mass. And here you can exactly observe the pattern that I have described before when we discussed this Keh-Fei interpolation formula, that if you change the valence quark mass and leave the C-quark mass constant, there's a fundamentally different behavior than if you change the C-quark mass. Right, and because we have this strong constraint in the chiral limit that the nucleon double moment has to vanish, our results has very, very tiny error bars actually. So these are results that we have for the neutron and the proton.
And, what order of magnitude is that compared to current experimental results?
That's hard to say because it still has theta bar in it. I mean, from this result, we can basically conclude how small theta bar has to be.
I see.
Okay. Yeah.
The thing is the magnitude of that absolute value. So a part in 1,000. Okay, 0.004.
Right.
That's very, very challenging calculation on lattice. And the way that we achieve this is because we don't zero out 0. So all the error goes up. It shrinks basically due to interpolation. You took Clover and other people's calculation or goes up because there is no control of the zero part mass. So you have to go to the continuum limit first before you do the chiral extrapolations. So all the other error bars you will show up.
Yeah, there will be a plot on that later.
10 times larger.
So because it's precisely 0 at the continuum, right?
Right. This is why I was telling so much about the anomalous water density and so on, because this is where the precision comes from.
You look at other cases that other people calculate GA is 1 point something. Here it is 3 orders of magnitude smaller. And that's very challenging. The most challenging thing
That's the question. These are, you said overlap on overlap, right?
No, it's overlap on domain wall. Okay, yeah, I missed that. The gauge ensembles control. Yeah, right. Sorry, I missed the point. Yeah, the gauge ensembles of RBC, they use domain wall fermions, but they also have very different chiral symmetry.
So it's domain wall in the C sector and overlap in the valence.
Right.
There's a little mismatch
Yeah.
Andre wrote and so on, and that is very small. We calculate the mismatch is the smallest. This combination, order of magnitude smaller than the other matches. Take the valence, other combinations.
Right.
Right.
And the mismatch goes away as order E squared. So, but that coefficient can be measured as order of magnitude smaller.
Okay. There's only one point left that I have to mention here. I mean, the final result that we have so far completely relies on our interpolation ansatz. And what we still have to do is, and what we do right now by adding this additional simulation system, to check that everything is consistent by simulating directly at physical masses. Okay, yeah, I mean, here is the same plot again for the case of the proton. Qualitatively, it looks the same. Right, and here is some comparison with what other collaborations get. So the red point is our result here for the neutron and the proton. And yeah, I mean, as Keh-Fei was mentioning before, if you carry out these calculations, for instance, with Clover fermions like Los Alamos groups do, they have to extrapolate. You have the data, you have the region where you're interested in, and you have no constraint behind it that basically leads to an increase of the error bar, not to a decrease, like in our case, where the chiral limit is fixed, basically.
With still just like comparing.
Mhm.
It looks like in the neutron, you're more or less consistent with the other collaboration.
Yeah.
Why is Los Alamos so different? Protons?
It's not that different because the error bar,
Yeah.
you need to multiply that by 3.
Oh, you're saying that should be okay.
Yeah.
Okay.
So it's
I
not
understand.
actually discrepancy. If you multiply it by 3,
I
then
see.
just
Yeah.
for showing the value in a single plot, we manually shrink the error bar by 3 times.
I see.
I guess
Right.
otherwise their error bar would be like.
Yeah,
the
it's
entire
would be hard to plot here. Yeah.
What is not plotted, you can see the blue looks like fine as a Schindler's calculation, which is
Yeah.
2 sigma,
Okay.
but they only have a statistic errors.
Mhm.
In our case, as you said, from this, we have a 10 sigma in the statistical errors, and then 4 sigma, 5 sigmas for the statistical, that make it a total of 4 sigma. So on the plot, it doesn't look like that different, but if you consider, if Schindler could consider, systematic errors, very different.
Okay. Then just this is the last slide I have. Can carry out the same analysis for the anomalous pi and n coupling. And of course, it's a bit simpler because we don't have this complex structure in terms of form factors here. But yeah, we can basically apply the same interpolation ansatz and similarly different quark masses. And this is the value that we get. We have the same plots as before for the EDM for neutron and proton. Yeah, this is the value we get. Also very, very precise. And when I say it's also consistent with the SU3 Chi-PT value by Andres collaborators that I've shown you before.
I have a quick question.
Yeah.
I think I missed this the first time, but how do you interpret the second plot with the curves? So is it
That's a combined fit. They have basically, you make a 2D fit with respect to the valence of the C quark. And it's just projected in one plot.
Do you have a good explanation as to why the purple is so qualitatively different from the other 3 colors?
The purple one is the overall.
Yeah.
Oh,
Yeah, so basically the purple line is the unitary case, basically where ms equals mv. Yeah. Right. Yeah, this is basically, this is unitary only. You see the error bar is a bit larger, but here if you consider the full ansatz with respect to C and the valence quark mass, then, it increases the quality of the fit again.
You can check the error bars. We don't have a systematic errors at this moment being analyzed. You can see the statistical error is three times smaller than our transfers. This calculation, this part is very stable. The error bar is very small. You can see that's part in 30 or something, 3%. Just a question: is there a theta bar for the second?
Yeah, probably. There must be a theta bar. Yeah, right. Sorry. Yeah, that happened several times, I think. No, there's always a theta bar. We do not know theta bar, and this is why we do not know the value without theta bar. Yeah.
I have one more question.
Yeah.
So as the mass of the C quarks and valence quarks, as that gap decreases, like if you had another curve with an even smaller gap, I think is what it looks like. So something like 0.2 GeV. If you had a curve like that, would it be closer?
Okay. You mean a different trajectory for different C quark mass or what?
Yeah. So like, it seems like the colors, if I can see right, I'm kind of colorblind. But
Oh, sorry.
if you're
Yeah.
going from the what is that, green to the like?
Yeah. Right. Right. If you this is basically what the answer tells us. If you decrease the C quark mass, you approach 0.
Okay.
Yeah.
and the valence squad mass
That's the opposite direction.
drives it away. Yeah. So this is what we have. I mean, this is exactly the trend that we see here.
This is the, as far as I can tell, this is the first time that people look at the power provision theory and valence is equal in opposite directions. All the others seems to be in the same direction. This is very surprising because it's the formula. He says there's a different sides. You know, there's one is proportional to C mass, the other is a valence mass, the other a different side in kind of provision theory. Earlier, Jan Liao says, "Oh, we must have done something wrong," which is totally off. It's totally wrong. This is a different direction until we found the partially quench confirmation formula that seems to support this. I still don't know why. Why would the valence C is interesting? Of course, that has to be because of cosine valence. No idea. No idea.
Further questions? Because I mean, after that slide, there's only the summary, so we're already at the end. If you have further questions, we have time, I think.
So this last point where you say consistent with SU3 type T.
Yeah.
For your extrapolation expression, is that also in SU3 or is that SU2?
That's hard to speak. I mean, we do not have exact planar symmetry. We have 2 + 1 in our case. I mean, so two degenerate quark masses for U and D and one strange quark mass. So there, I mean, in that context, there is no one-to-one correspondence to that.
SU2 + 1.
Yeah, basically.
Not SU3.
Yeah. But I mean, anyway, I mean, the results are the same within the error also.
But we do not explicitly show SU3 symmetry in the fitting form, right? Extrapolation, right? We just have some numbers.
No. That's, I mean, the fit form is from heavy bio.
Yeah, it's related but not explicitly derived.
I think in fact the theory you count maybe SU2 because I don't think they involve straight.
Yeah, I'm not an expert on heavy carbon.
Just SU2 carbonization theory. And there's no strange in that formula there.
I think the result from Savage is.
Yes,
I think that's SU2.
Okay.
Yes, with presumably you can get SU2, but it's with the valence C is already complicated enough. You look at another C flavor, it's different.
Yeah. All right.
But it will be interesting to see the carbonization theory, which I'm not that familiar with, to see the formulas and why do they have the same different side. That will be a physical question, not just mathematical. Is there physics that shows that they will behave differently?
Okay, yeah, let me just summarize. So, as I said, study of the QCD-Lagrangian can help to understand CP-violation within and beyond the standard model. There are some proxy observables to study, namely nucleon EDMs and CP-violating binary coupling. So both of you have shown the results. Can be studied in the lattice. Color symmetry and enormous volatility, in particular, are crucial features in order to carry out lattice calculations successfully. This is why we use overlap fermions, the domain of gauge ensembles. Yeah, I've shown you already our results as they look up to now. Yeah, and as I said, what we have to do, what we are doing basically right now is to include additional runs in order to cross-check our interpolation, namely by evaluating the matrix element at physical final masses. Right, this brings me to the end. Thank you for that. Any questions left?
I just want to comment on the last slide, the extrapolation to physical biomass, it should be adding one more point or several more points, which is a physical unitary mass with the ensemble C quark, which has physical.
Sorry, I did not get it.
So yeah, I just make sure you said extrapolate to physical biomass.
Yeah.
Is that C or valence you're referring to? I mean, the next slide.
Ah,
For both C.
Yeah, for physical biomasses, you're saying on an ensemble with
yeah,
physical C quark.
yeah,
Physical
yeah,
biomass,
yeah.
and we want to also have the valence quark.
yeah, of course. So, I mean, there would be, in plots like that, the point would be on the top, but also different, also another trajectory that goes through here.
Yeah.
Yeah.
You can have a valence below the C biomass.
Yeah, of
Below
course,
the
of course,
physical
yeah. If you want to do that.
Well, why not? The thing is just see
Yeah.
how behavior,
Yeah.
how it behaves. But there is a danger when you have a valence C mass, lower than the C mass, you have some ghosts which can show up. And that will be the ghost of the partial quench carbonation theory will show that this strange behavior. That would be dangerous. Other questions?